Let's now look at buffered solution of a weak base. Buffered solutions also can be formed from a weak base and the corresponding conjugate acid. In these solutions, the weak base B reacts with the added hydrogen ions. So this is a reaction, base plus the hydrogen ions added, then forms the conjugate acid BH plus. And the conjugate acid BH will then react with the hydroxide ions as follows. BH plus the hydroxide ions forms the base plus water. So the approach needed to calculate or to perform pH calculations is identical to the one we used earlier in our calculations. Remember, the first one we used a strong base, sodium hydroxide, was added to a buffered solution of a weak acid. Okay, so the approach is similar. Okay, so now we can look at an example. Let's see how we can perform pH calculations when an acid is added to a buffered solution of a weak base and its salt. Okay, so let's have an example. So this example is about the pH of a buffered solution. The pH of a buffered solution. A buffered solution contains contains 0.25 molar ammonia. Then Kb for ammonia is equal to 1.8 times 10 to the power negative 5, and 0.4 and 0.40 molar ammonium chloride. Calculate the pH of this solution. Okay, so there are two ways that we can use to calculate the pH of this solution. Okay, so the first one we can use the ICE. So let's first use the ICE table. Then we are going to compare the results. Okay, so let's use the ICE table. Okay, so first of all, you can determine the major species. So the major species in this solution are, so we are going to determine the major species. So make sure you know that there's ammonia and ammonium chloride. So we expect to have the chloride ion, ammonium ion, water, and water. Okay, so these are the major species: ammonia, ammonium ion, chloride ion, and water. Okay, so from these now you determine those that will participate in the equilibrium. Okay, so now chloride ion is a weak base. This one is a weak. Chloride ion is a weak base. Then water is a weak base, or acid. Okay, so these two will not participate in the equilibrium. So we are just going to look at the important equilibrium. So the important equilibrium for this reaction is ammonia. This one, ammonia plus water, then will give us ammonium ion. Plus hydroxide ion. Okay, so this is the important equilibrium. Okay, so from this now we can come up with the ICE table. So let's determine the concentrations. Okay, ICE. The concentration of ammonia, initial concentration, that is 0.25 molar for water. In fact, water is not even involved. You can just put a dash. Then for ammonium ion, that is 0.40. Then for hydroxide ion, that is 0. Okay. Then change minus X plus X plus X. Equilibrium 0.25 minus X, 0.40 plus X, then X. Okay, so these are the equilibrium concentrations. Then now we'll need to determine the value of X. Remember, in the question, we've been given KB. Okay. So, we'll work it around KB. Our KB given, KB is equal to 1.8 times 10 to the power negative 5, which is equal to, KB is equal to concentration of ammonia, this one, ammonium ion, concentration of ammonium ion times concentration of hydroxide ion over concentration of ammonia. Okay, so now we can substitute the equilibrium concentrations. So we have 1.8 times 10 to the power negative 5 is equal to concentration of ammonium ion, which is 0.40 plus X, then concentration of hydroxide ion, which is X, over concentration of ammonia, 0.25 minus X. Okay, so we now use the assumption that X is so small, so therefore we can neglect X. by applying the 5% rule. Okay, so this x is so small compared to these values. Okay, so we have 0.40 x over 0.25. Okay, so you can say the approximations are valid. The approximations are valid by 5% rule. Okay, so we can now solve for x. So you can divide there, then afterwards you find x. You simply divide that figure into the KB, Okay, so in this case, when you divide, you are going to find that x is equal to 1.1 times 10 to the power negative 5. So this is the value of x. Okay, so now when we go to the table, the value of x corresponds to hydroxide ions. Okay, hydroxide ion concentration is equal to x from the table, so which is now equal to 1.1 times 10 to the power negative 5. Okay, so here, okay, should be like that. So this is the concentration of hydroxide ion, 1.1 times 10 to the power negative 5. So if you know the concentration of hydroxide ion, then you can straight away calculate the concentration of hydrogen ions, which will help you now to calculate the pH. Okay, so we can find the pOH. So let's determine the pOH. So pOH will equal to negative log 1.1 times 10 to the power negative 5, which will now give us the pOH in this case will be 4.95. This is the pOH. Then now we know that pH. We know that pH plus pOH is equal to 14.00. Straight away we can find pH. So pH will equal to 14.00 minus pOH. Okay, so in this case we know our pOH, so it will be 14.00 minus 4.95, which will now give us when you subtract, you are going to get 9.05. Okay, so you can see that this pH is greater than 7. So it's not acidic, it's basic. Okay, so this is how we can calculate the pH of this solution. So this is our pH, 9.05. Okay, so now we can also have an alternative. So let's see how we can calculate. Remember, we mentioned that you can as well use the Henderson equation, Henderson-Hasselbalch equation, to calculate the pH. Okay, so let's now apply the Henderson-Hasselbalch equation to determine the pH of this basic buffered solution. Okay, so we know that pH is equal to pKa plus log base over acid concentration. So now in this case we do not have Ka. What has been given is Kb. So now we need to convert Kb to Ka using the relation. So Ka times Kb is equal to Kw. This is the equation. Okay, so Kw, we know the value of Kw, that is 1.0 times 10 to the power negative 14. So Ka will equal to Kw over Kb, which is equal to 1.0 times 10 to the power negative 14 over Kb, which is 1.8 times 10 to the power negative 5, which will now give us our Ka. So when you do the computation, you get you are going to get 5.6 times 10. 5.6 times 10 to the power negative 10. So that is our Ka value. Okay, then if we know Ka, then we can apply now the Henderson-Hasselbalch equation. So first of all, let's find the pKa. So pKa will now equal to log 5.6 times 10 to the power negative 10, which will give us 9.25. So that is our pKa, the one that we shall use in the equation. Okay, so now we have pH will equal to pKa 9.25, then plus log base concentration, which is we take ammonia, this one, ammonia, okay, which is 0.25 molar, over acid concentration 0.40 molar. Okay, so you divide there, now you find the log. So when you divide, we are going to have 9.25 plus log 0.625, which is equal to 9.25 minus 0.20. Okay, so when you subtract 9.25 minus 0.20, you are going to get 9.05 as our pH. Okay, so you compare this with the one that we found earlier using the IC table. You can clearly see that the pH is the same. Okay, so it's your choice to choose. You need to choose which method you can use to determine the pH. Either you can use the IC table or the Henderson-Hasselbalch equation. So it depends which one is simple for you. Okay, so you can use either method since it will give you the same pH. Okay, all right, so that is how we can calculate the pH of a weak base. All right, so now we can look at we are now going to look at the buffering capacity. Buffering capacity. Buffering capacity. Okay, so we first define the buffering capacity. The buffering capacity of a buffered solution represents the amount of protons or hydroxide ions. Amount of protons. Amount of protons or hydroxide ions. Or hydroxide ions the buffer can absorb. The buffer can absorb. The buffer can absorb without a significant change. Without a significant change. Without a significant change in pH. Okay, so that is how we can define buffering capacity. Okay, so a buffer with a large capacity contains large concentrations. A buffer with a large capacity contains large concentrations of buffering components. Okay, it contains large concentrations of buffering components. And so can absorb a relative large amount of protons or hydroxide ions and show little change. So this buffer, which has large concentrations, can absorb a large amount of protons, can absorb large amounts of protons or hydroxide ions and show very little change. Okay, so the pH of a buffered solution is determined. Remember when we looked at the Henderson-Hasselbalch equation. So we determine the pH of a buffered solution is determined by the ratio. Of the conjugate base over conjugate acid, this ratio. Okay, so when we write the Henderson-Hasselbalch equation, which is this one, okay, base over acid. So this ratio of the conjugate base and acid is the one that determines the pH of a buffered solution. Okay, then the capacity of a buffer, the capacity of a buffered solution. The capacity of a buffered solution is determined by the magnitudes. Determined by the magnitudes of HA and A minus. Okay, so we'll look at how large it is. Okay, so you find that a buffer with a larger capacity, will absorb more protons or hydroxide ions and show little change. But one with a small capacity will absorb little and show some pH changes. Okay, so we can now look at an example. Let's compare two buffering solutions, two buffered solutions. We are now going to add a strong acid to a buffered solution. We want to see the changes that will occur. Okay, so in this example, we are adding a strong acid, to a buffered solution. Adding a strong acid to a buffered solution. Calculate the change. Calculate the change in pH. Calculate the change in pH that occurs when 0.010 more gaseous HCl is added to 1.0 liter of each of the following solutions. Solutions. Okay, so we have two solutions. We have solution A and solution B. So solution A is 5.00 molar. 5.00 molar acetic acid. 5.00 molar acetic acid and 5.00 molar sodium acetate. Okay, that's sodium acetate. Then now solution B. We have 0.050 molar acetic acid and 0.050 molar sodium acetate. Okay, so we want to see then also for acetic acid, Ka for acetic acid is equal to 1.8 times 10 to the power negative 5. Okay, so that's a Ka for acetic acid. So we want to see the changes that will occur when we add 0.01 more of gaseous HCl to each of these solutions, solution A and solution B. Okay, so now solution. So the first step is to calculate the pH of these two solutions, solution A and solution B. before the addition of the acid. Okay, so first of all, we calculate the initial pH, the original pH before the addition of the gaseous HCl. Okay, so we can calculate the pH using the Henderson-Hasselbalch equation. So pH is equal to pKa plus log. So in this case, we know the conjugate base, which is C2H3O2, okay, base over acid. Our acid is acetic acid, C2H3O2. Okay, so we can calculate the pH using this relation. Then now, for both solutions, the initial pH can be calculated by this. Okay, we are going to use the Henderson-Hasselbalch equation. So clearly you can see that the concentration of the acid and the conjugate base is the same. So the concentration of the acid, this one, concentration of the acid, and this is the same. Concentration of the conjugate base and the acid is the same for both solutions. So C2H3O2 is equal to the concentration of the acid. Is equal to the concentration of the acid in both solutions. Okay, so you can clearly see that. So remember, we mentioned that if the ratio of the base and acid is the same, it means the solutions will have the same pH. So here it means that the pH of solution A is equal to the pH of solution B. Okay. Since in both cases we are going to find 1, log 1, which is equal to 0. Okay, so pH is equal to pKa. So in this case we can determine the pKa. So negative log that pKa of 1.8 times 10 to the power negative 5, which is giving us 4.47. Okay, so our pKa is 4.74 as the pKa. Okay, then plus log. In both cases, the ratio is giving us 1. Okay, so if you divide 5.00 molar over 5.00 molar, this one for the salt of the conjugate base, 5.00 molar times over 5.00 molar, you are getting 1 in the first solution, in solution A. Then again, when you divide 0.05 molar over this, you are getting 1. Okay, so in both cases, the pH in this case, so the pH, since here you get a 0, log 1 is 0. So pH is equal to pKa, which is equal to 4.74 for both solutions A and B. Okay, so this is the initial pH. The initial pH for both solutions. Then we are now going to add 0.010 moles of HCl and see what will happen. Okay, so now let's add. Since we know the pH of both solutions A and B, which is the same, 4.74. Okay, so now when we add HCl, when we add HCl, it means we are introducing hydrogen ions into the system. Okay, so now the hydrogen ions, remember the acetic acid is a weak acid, and these hydrogen ions, we have high affinity for the conjugate base. Okay, so the reaction that will occur is hydrogen ions plus the conjugate base C2H3O2, then will form, it's going to form acetic acid. Okay, the acetic acid will be formed. So this is the equation the reaction that will occur. Okay, so now from this we are now going to determine the concentration. And remember, HCl is a strong electrolyte, it completely ionizes. So the concentration of HCl, and remember 0.01 is dissolved in 1 liter, so it's equal to the molarity. Okay, so before reaction, so we determine, and after reaction. Okay, so before the reaction, remember we are adding 0.010 mole of HCl in 1.0 liter. So moles equals to molarity. In this case, we know that N is equal to mV, molarity times volume. So we have 0.010 molar. We can include we can work in moles or molarities, just one and the same. Okay, so we have this as the molarity of the acid before the reaction. Then we have so for solution A now. So let's look for solution. So we are going to solve this question separately. So we have solution A. We are solving now for solution A, the changes that will occur in solution A. Then we'll compare with the changes that will occur in solution B. So for solution A, the initial concentration is 5.00. The initial concentration is 5.00 as well. Okay, so since the acid will react to be completely consumed by the base. Okay, so the acid will react with the base, so nothing will remain. So we have 0 after reaction. Then now you subtract from 5. So it is now 5 minus 0.01. You are going to get 4.99. Okay, then we expect the concentration of the acid to increase. So this one now go to 5.01 molar. Okay, since we are adding more hydrogen ions, so expect the acidity to increase. Okay, so from there now, we will need to determine the new pH. Since we have the concentration of the base and the acid. So now let's determine the new pH. So new pH for solution A. New pH for solution A, we'll use the Henderson-Hasselbalch equation, pKa plus log base over acid. So in this case, This is our conjugate base, okay, which is the concentration is 4.99 over concentration of the acid 5.001. Okay, so we divide that number and find the log. Okay, so our pKa, the one we found is 4.74, then plus log, so in this case it will give us a negative value when you find the log, negative 0.0017. Okay, so that is the log that you find when you divide those two numbers, 4.99 over 5.01. So when you subtract, you are going to get 4.774. Okay, so that is the pH of solution A. Okay, so now we can see that the pH for solution A has not changed. Remember the pH that we found at first for solution A and B is 4.74. So for solution A there is no change. The buffer has resisted the change in its pH. Then let's do the same for solution B. Okay, so take note of the new pH that we have found for A, which is 7. So new pH for A. So new pH for A, that is 4.774. Okay, so we do the same now for solution B. So we are now going to solution B. Okay, we do the same. We need to find the new pH for solution B. Okay, so the moles added 0.01. Then the concentration of the base for A 0.050. Then the concentration of the acid, which is the same, 0.050. Okay, so this will be consumed, 0 will remain. Okay, then now this minus that, since the acid is being consumed by the base, we are going to have 0.040. Then this one will increase it to 0.060. So these are the new equilibrium concentrations. Then now we calculate pH. So pH is equal to pKa, which is 4.74, plus log for the base 0.040 over 0.060. Okay, so when you divide and find the log, so it will be 4.74 minus 0.18, which will give us 4.56 as the new pH. Okay, so for solution A, new pH is 4.74. Then for B, it has gone to 4.56. Okay, so although the pH change for solution B is small, a change did occur, which is in contrast to solution A. So these results show that solution A, which contains much larger quantities of buffering components, has a higher buffering capacity than A. Okay, so now you can see this one, solution A has a larger buffering capacity. I explained this area, buffering capacity. So the one with a larger buffering capacity will absorb a large amount of protons and show little change in its pH. But this one is less, so it will show some changes in the pH. So the one with a larger buffering capacity absorbs more protons or hydroxide ions and show very little change. Okay, so that is how we can calculate the pH when an acid is added to a buffered solution of a weak base. Okay, so the next thing that you need to look at are titration and titrations and pH curves. Titrations and pH curves. So a titration is commonly used to determine the amount of base or acid in a solution. Okay, so this process involves a solution of known concentration. So a solution of known concentration is called the titrant. Okay, the one that goes into the burette, that's called the titrant. Then the unknown concentration is called the analyte, the one that you put in the conical flask. Okay, so suppose this is your burette. You are carrying out some titrations. Okay, this is just a sketch of a burette. Okay, burette, then you clamp it using a clamp and stand. Okay, then here you are going to have a conical flask down. You titrate against a white background. Okay, so what you have here is what we call the titrant. The titrant, it could be a strong acid or a strong base, or vice versa. Okay, sometimes the analyte can be an acid or a base. It depends with the type of reaction that you are carrying out. Okay, so this one is known, this one is unknown. So now you want to determine. So this process is what we call the titration. So for an acid base titration, you need to use an indicator. The one now which you indicate it will show the end point. Okay, by changing its color. So the common indicator we use in acid base titration is phenolphthalein, which is colorless in acid solution and pink in base. Okay, so this one it will be continued. We can end here on then also at your free time you can look at strong acid and strong base titration curves. So these are straightforward. We know that moles is equal to molarity times volume. Okay, so it's very easy to calculate the concentration. There's nothing complicated. Okay, so that's all about acid base equilibria. Then the rest you can study on your own. Thank you.